the Routh Hurwitz criterion. And let me use give you one formulas, and then I use a few examples to demonstrate calculations. So if we are given a template of the characteristic equations, and we're starting from characteristic equation here. So here, let me use symbols, the coefficients. Okay, so here I will pay attention is about the coefficients of each term. And the Routh Hurwitz criterion basically just utilize those coefficients for calculations. And here come to the key step. So right now we put into those coefficients into a table. And we're starting from the highest power, and then we go to the second less degree in the decreasing orders as n minus 2. And here we're going to lay down to the S0 here, okay? And the tabulations for this is like this. You looking at the coefficient from the highest degrees, and you arrange the coefficient like this. an minus 1, and an minus 2, and then an minus 3. So basically you do this kind of the jump-wise arrangement. And if there is any zero coefficient, you just put into 0. Okay, so here, let me get one more. Okay, and you keep writing until you meet the A0 here. So due to the arrangement, sometimes the final term A0 will be here, sometimes the A0 will be on the second row here. Okay. So we have this is a given one. Then we begin to develop the calculation of these tables, and the calculation is based upon the formula. The formula is this. For this one, and look at here carefully. For this one, basically is this, taking this as the pivot and divide by that numbers. Okay. And then the numerator is multiplications of this an minus 1 times an minus 2 minus, let me use color to denote this is a minus, minus an minus 3. Okay. And for this one, this is the first column here. For the second column, and again, we have in the similar pattern using an minus 1 in the denominators. And for the second one, this one is this. We're taking multiplication of the two numbers, an minus 1 times an minus 4, and minus, let me write one more here, an minus 5, minus this one. Okay. So this is on the second column. So you repeat. Sorry, here I try to make space. So you repeat these things until going to 0. Okay. And then to the third one, and as n minus 3. Repeating the same patterns. For this one, and not allow me to write this one. So basically the denominator is the same. You use the upper one as a pivot. So say, let me make one. So let me, how about this? So let me say this is, let's just make one symbol, okay? So here is, for example, B1 here. So let me make this one as the B2. Okay, so here for this one, taking the same template, using B1 as a pivot, and then for this one is B1 follow the same pattern here. The B1 multiplied with A minus 3, okay, and minus B2 multiplied with this one, AN minus 1 times B2. Are you able to see it? Repeating the same templates like we did so basically right now for this one, you're simply working on the top 2 rows and repeating the same templates like this one. Okay? Okay, so repeating the same thing here. And until you finish all the things, and then the S0 should be a single term here, whatever. Okay? And once we have this one, then the Routh Hurwitz criterion saying is the number, here probably you can use your own words to write down the criterion. We're looking at the first column for whatever the calculation is. We'll only look at the first column, and right now the first column will be numbers once you've completed all the calculations. You're looking for the sign change from number to number, sign change of the numbers. The number of the sign change is equal to the number of the poles on the right-hand side. Okay? The number of the sign change is equal to the number of the poles on the right-hand side of the complex plane. So the best way for us is this. We wish our calculation of the certain system, they don't have sign change, which means all the poles on the left-hand side. We wish, because we don't want the system to be unstable. If we don't want the system to be unstable, so we wish that system will have the calculation, we call it, this one is called the Routh Hurwitz, the column. We wish this column has no sign change. So that will guarantee, okay, there's no holes on the right-hand side. Okay? So we can use one example to look at the calculation. And you don't need to, every time you don't need to apply the Routh Hurwitz criterion if you are able to directly calculate the roots. If you are able to directly calculate the roots, then you don't need to apply this criterion. Because if you are able to calculate the roots, then right away you can tell the system is stable or not. But sometimes if the polynomial equation, the characteristic equation is a higher degree, like this, and for this kind of higher degree, if this is a 6th order degree system, the 6th order system, for this one is sometimes will be hard at the first moment to determine what are the roots, right? So which means that will be, unless we can go to MATLAB become available or handy. Otherwise, if you don't have those tools available, then you can just use this criterion. So for this example, we can see and x6, x5, and then we arrange 1, 4, and 3, 2, 1, 4, and 4. Okay. And then we begin to build up these tables here. So to the fourth power, the first one we do the calculation is this 4, and then this is the 4 times 3, 12, and minus 2. Okay. So this one, let me write a smaller 12 minus 2. So this one is 2.5. Okay, and then the second one is the 4, and again multiplication of the two numbers, and 4 minus multiplication of this one. So this one is equal to 0. The third one, again, let me write smaller. third one, again, is 4, and then multiplication of the two numbers is 16 minus this one. So basically here is nothing. Okay, so here is 0. So here is 4. Okay. And for the third one, right now repeating the same thing. So here we use this one, the above one as the denominator of 2.5. And then 2.5 multiplication of this one equal to 5 minus this one, 0. So that is equal to 2. And for the second one, 2.5. How many minutes we have for today? 5. Okay. We can complete this example. So here, this one will be 2.5 multiplied 4 is 10. And minus here is 16. So that will be equal to minus 2.4. Okay. And then for the last one is again 2.5. This one we multiply. This one is 0. And then this one come to here is 0. So here the last one is 0. Okay, we stop at 0 here. So as 2, then repeating, so that will be 2, and multiplication of this one is 0, minus multiplication of this. 2.4 times 2.5 is 6, and that is minus 3. Sorry. You see I made a mistake? This value is 0 minus of the multiplication of the two numbers, and 0 minus minus 6, right? Yeah. Okay, that should be positive 3. So here okay. And for this one is 2, and then multiplication of the 2 is 8 minus 0, and which is 4. And here, if you can continue, you can see that should be equal to 0. S1. So here for S1, we have 3. Multiplication of the two numbers is minus 7.2, and minus this one, 8, equal to 15.2 divided by 3, and whatever, 3, 15.2, okay? So for this one is 0, because multiplication of the 2 minus this one, okay? So S0 is, you can repeat, this one is minus 15.2 divided by 3, and multiplication of the two numbers, 4 times minus 15.2 divided by 3, and minus 0. So here is 4. Okay? So right now we have built up these tables, and that is for demonstration. You don't have to draw those kind of lines, and if you get familiar with the whole process. Okay, right now let me label the numbers on the first column. 1, 4, 2.5, 2, 3, minus negative numbers here. So those are the numbers appear on the first column, and which sometimes people refer this column as the Routh Hurwitz column. Okay, and from here you can see how many sign change. From here we have no sign change, no sign change. Between 0, 1, and 4, and from 4 to here, no sign change. Here there is no sign change, no sign change. But here we have 1 sign change. From here, again, we have 2 sign change. So in total, we have 2 sign changes. So here we can pretty much guarantee there's a 2 poles on the right-hand side. The system definitely unstable. Okay, and this can tell us the numbers, but wouldn't tell us what are the location of the poles unless we solve for this one. But this criterion won't provide us this solution. Okay, so today we stop here, and pretty much I think you should be able to finish your homework, the question 4, okay, from today's techniques. Thank you.